Sounds good. Good morning. My name is John Stone, and I'm the main developer of VMD. And my goal this morning is to introduce some of the features of VMD that you may be less familiar with, and to answer questions you may have about the general features of VMD or things that are sort of beyond what's in the usual tutorial materials. So VMD is used for basically preparing both structures, simulations, and analyzing and visualizing the results of those simulations. VMD works with all the major molecular dynamics packages. It also works with lattice cell simulations, quantum chemistry calculations, and it has a lot of features for working with experimental structure data such as cryo-EM density maps, tomograms, and so on. So you've seen probably the main VMD tutorial. There are quite a few other VMD tutorials, so I'd advise everybody to have a look at those other tutorials. Many of them sort of talk on specialized topics, and they have examples that are pertain to particular types of calculations or software packages. And so I'd advise everybody to have a look at those when they're finished looking at the main VMD tutorial. So if you think about where VMD sits in its role, it's sort of a go-between between experimental structure information and the different simulation packages. I like this little diagram because it shows VMD sort of in between the different tools. It's sort of a nexus within which you can do a lot of the different steps that you need to work on when you're doing your simulations. Some of the things that we've been working on in terms of extending VMD have been to add more tools in VMD to work with hybrid modeling protocols, things that combine cryo-EM structure information with X-ray crystallography and various other modalities of both computational structure prediction methods and simulation methods. We've put a lot of effort into improving the visualization features of VMD, and that's one of the things I'll show you some examples of later this morning. And I think you'll see some nice demonstrations from Mariano also later this morning. The main thing that VMD tries to accomplish, if you look at the big picture, are to make good, easy connections between all of the different software packages. So one of VMD's key strengths is that it can read and write the majority of the mainstream simulation input and output files that the different packages read and write. And this allows you to easily visualize those structures, to use VMD both as a tool for preparing your input, but also for debugging what's going on in those simulations and to check that things are working the way that you expect them to. Some of the things that we're very happy with in VMD are, the lion's share of the graphical interfaces that people work with, especially the plugins. A lot of these things are actually implemented as scripts. Those are open source. You can actually go read the source code for any of these tools, and you can adapt those tools to make your own customized versions if you do specialized research of some sort, or you need to make tools that are sort of customized for the particular tasks that you're doing in your work. And so a lot of the things that VMD has can be reused for other purposes. And so I advise people to have a look at that. They might find that very interesting. If you develop your own simulation tools, VMD is very extensible. It has a so-called plugin mechanism, not only for writing graphical user interfaces, but also for things like reading and writing molecular data files. So if your laboratory develops their own simulation codes or other types of tools or databases, you can write plugins that teach VMD how to directly read and write even specialized file formats that are developed within your own laboratory. And so that's something that's sort of unique about VMD when compared to other tools. Some of these extensions are quite extensive. So as an example, I think, Mariano, are you going to be showing them QuickMD in greater detail, or did Raphael do that earlier in the week?
We did that on Monday.
Okay, great. So So just as an example, although it's an extension, I mean, this is technically, it's a plugin to VMD. So yet it's just one of these examples that's written as a script actually. But QuickMD, as you've already seen, it sort of encapsulates an entire workflow for preparing, visualizing, and analyzing simulations. And it's actually implemented as a script, and you can actually read the code and see how it works. I think one of the things that's particularly noteworthy about QuickMD is something that we're trying to build into other tools, is the ability to log all the steps that you take when you're preparing your simulations or analyzing them, so that you can make the work that you're doing more reproducible, so that people can essentially share what they're doing with other users in their laboratory more easily, and to help you, in the longer term over the course of a project, be able to repeat or remember exactly what steps you took in a long simulation campaign. Here I'm showing a list of a large number. It's not even all. It's many of the plugins that are in VMD. And what's interesting here is if you look at this large list of extensions to VMD, the ones that are highlighted in green are actually developed by external teams or external contributors, other laboratories around the world. So, the different tools that are included with VMD, many of them were developed here at University of Illinois, but many of them were also contributed by outside groups. And so if you develop a tool that you think is widely useful to a broad range of users, this is something we're happy to talk to you about. If you want to contribute new tools, or if you have suggestions for improving them, because these things are all open source, these are easy things to do. Aside from sort of the graphical interfaces and things that people are probably already familiar with in VMD, VMD can be run in a text mode, and it can be run in parallel. And so that allows you to do very large scale analysis calculations on supercomputers. This is something that most people are probably not aware of. So for example, we took a calculation that once upon a time, this would have taken 5 years if we had run it on a conventional desktop computer. This is for calculating so-called cross correlations between hybrid fitting simulations, where we take an X-ray crystal structure and we fit it into a cryo-electron density map. And by doing this, we're basically able to get the atomic detail structures from crystallography and bring that atomic detail into the natural conformations that are captured by cryo-EM. One of the key things we have to do when we do a simulation like this with a hybrid fitting simulation is to be able to measure the quality of fit between the atomic structure and the experimental density map. And that's what this algorithm does. And just as an example, putting this calculation onto a very large rabbit hemorrhagic disease virus simulation, if we do that calculation for the entire structure, but also individually for every single one of these repeated subunits and the different little monomers and the icosahedral virus structure, we get a large number of these calculations. So we have 10,000 frames over the course of the simulation. We want to evaluate that for 720 components of the virus structure. And if we ran that again as a serial calculation, it would take 5 years. So this is a case where we'd like to use the parallel computer to speed it up. If we use a new GPU accelerated algorithm that we developed in VMD, we can take that 5 years and bring it down to 14 days. So using the power of GPUs, we get a tremendous speed up. But even with the GPU, that we'd want it to go faster yet. So 2 weeks is better than 5 years, but we want it to go faster yet. So by doing this calculation in parallel and basically decomposing this problem space, both in terms of trajectory frames and the different atom selections on the virus capsid, we can do that calculation on 128 nodes in only 3 hours. So that's a factor of 105 speed up over the single GPU node. And if we run on 2000 nodes, we can bring that time down to 19 minutes. And so that's about a 1,000-fold speed up. That's about a 50% scaling efficiency, which is pretty good for a huge number of nodes. So that's a very impressive achievement. So you can, this is just one example. Anything that can be decomposed by trajectory frames, by atom selections, or by different types of calculations, measure commands in VMD, even things that you write in your own scripts. All of these things can be parallelized, and you can look at the VMD tutorial. In the later sections of the tutorial, there's some discussion about so-called parallel commands, and these parallel commands make it very easy to do different things by the node that's doing the work. So you can basically decompose the work according to the node, or you can use what we call a dynamic work scheduler to assign work on the fly, so that you don't have to even think about how many nodes there are. You just create a big list of the work to be done, and it can basically go through and crunch through the work dynamically. And VMD handles all of the message passing between the compute nodes for you, so you don't have to become an MPI programmer to accomplish these things. Aside from doing sort of your typical molecular calculations, another thing that VMD can do is it can calculate time varying properties in a volumetric map. So for example, this figure is showing time averaged spatial occupancy. So you can calculate probability density isosurfaces. This is showing the probability density for magnesium ions to occupy certain positions in space around this tRNA. There we go. Some of the other things that VMD has a lot of features for include large scale high-end rendering. So for example, if you want to render large movies, or if you have very large structures, VMD has powerful ray tracing engines built in. Just like with the parallel computing aspect for analysis, if you're rendering movies, you can use a cluster or a supercomputer to render those movies much faster by using multiple compute nodes. And so this is very helpful. For example, we rendered a movie that I'll tell you a bit about a little bit later in the talk. It had 18,000 frames. If we render that on one workstation, that can take quite a while. But if you use a large number of compute nodes or a cluster in your department, you can render even very long movies much more quickly. And so some of the things that make VMD sort of unique among the other molecular visualization tools is it has a bunch of different high-end rendering tools built into it. So these are ray tracing engines for CPUs, for GPUs. They have a lot of special features for advanced lighting, for drawing transparent surfaces with higher quality. Lots of things that are difficult to do interactively in OpenGL are very easy to do in these ray tracing engines. And so I'll show you a few examples. One of the key things that ray tracing engines can bring you is much higher quality rendering without a lot of work from the user. So if we look at the example on the left, if you're accustomed to your typical molecular visualization software, they use a very simple shading model like the virus capsid you see on the left. These two images both show a small satellite tobacco mosaic virus capsid that's been cut open, so it's cut in half. On the left, you can see with simple shading, it looks relatively flat. You can't discern the depth of the interior part of the virus capsid. It's hard to see any of the key structural features, the pockets, pores, and cavities that make up the surface of the virus capsid. If you look at the image on the right, doing nothing except for turning on the advanced rendering modes in VMD, you can get an image like this. This is using one feature, which is known as ambient occlusion lighting. If you just turn that on and render a figure with it, you'll go from a figure like the left to a figure like the one on the right. And this is much more informative. And the best part about it is that you don't have to manually position light sources or spend a lot of time adjusting things to get a figure like this. It's actually pretty easy to get a result like this. And so this is one of the things we've put energy into is developing rendering features that are not only able to produce high quality images, but that are very easy to use. So you don't have to become some sort of a graphics expert to be able to produce something like this. It's actually very easy. If we look at more conventional rendering of the same thing, so this is that satellite tobacco mosaic virus. It's cut open partially, and you can see the interior RNA. You can see the exterior of the virus capsid colored by radius. So, VMD has lots of different coloring schemes. Many of them have adjustable parameters so that you can define the range over which something is colored. if you look at the VMD graphical representation menu, there's a tab there called trajectory, and under that tab, there's an element called color scale data range. And so, for example, in this virus capsid picture, if we color something by radius, it would naturally start at a radius of 0. But in our case, we wanted to color everything in the interior with blue and not have it begin the color ramp until we get to the outer edge of the virus capsid, so that it sort of highlights with color as well as the shading the distance from the center of that capsid. And so that's what was done here. So if you use that color scale data range, you can put finer controls over the starting and ending values that are mapped to the colors that are shown in a visualization. VMD has a lot of different material properties. So when you create a visualization in VMD, you'll see that there's a material selection. These materials that are included in VMD are just built-in defaults. All of them can be edited. And, there are different types of transparent materials. For example, some just have a very simple transparent rendering scheme. Others, like the ones you see here, sort of are designed with a sort of edge outlining feature, so that rather than obscuring the interior of what the surface encloses, we can actually easily see the chlorophyll rings in this light harvesting complex. And so this is an example of the kinds of transparency that you can use in your own figures. There's a transparent material. Let's see, I'm trying to remember the name, that it gives you this sort of a look to it. And one of the things a lot of people use these materials for is to draw, for example, their water box in their simulation. So that's something I suggest people try and do. Try rendering the water box in your periodic cell. This is a nice thing to practice doing with the material properties in VMD. Some of the things that the ambient occlusion lighting is useful for, if you look at the different structures in these examples, I think they look more 3D with the lighting and shadows than they do when you use a simpler rendering mode. So these were all generated using the ray tracing engines in the render menu. And the example on the bottom left is using what we call depth of field, or so-called defocus blur. And basically what that is it gives you the opportunity to focus the camera in VMD on a particular part of your structure. And you can show that location in space with much higher detail. It's in crisp focus, and everything that's closer or farther away from that location will get progressively more blurry, just like with a real physical camera lens. And so that you can use this to draw the viewer's eye to a particular part of the structure, but you can leave the rest of the structure there for context. And they can see that the rest of the model is there, but it isn't distracting. So this is one of many such things that you can do when you're deciding how to visualize your models. You can use things like depth of field, focal blur. The way you choose your colors can affect how people look at the renderings that you produce. I was going to suggest that when you're choosing colors for VMD, there's a great set of applications that are available for free that are made by Adobe. They make some applications for choosing colors, and it'll give you suggestions on colors that are complementary so that you can have a nice color balance. And in fact, some of the apps, I think there's a phone app that you can use that will basically use the camera on the phone, and you can take a photo of something that you like if you have a particular painting or another visualization that you like, it'll analyze the colors in that image and suggest a palette of colors that either mirror what's in there or that give you something that's complementary. So that's something worth looking into. And sort of, even though it's sort of outside the scope of using VMD itself, there are a lot of these things that you can use to help you make better images. Some of the other examples of why you want to look into these more advanced rendering schemes in VMD, and one of the reasons why it's important that you use things like ambient occlusion lighting that are sort of automatic. This is a great example. This is the exterior of an HIV capsid, and if you look on the left, you can see that the HIV capsid is composed of a large number of these hexameric subunits, Each of the hexamers has a little pore in the center. And, you know, if you're showing this structure to somebody for the first time, they may not realize that there's a little poreless hole in each one of those hexamers. If you use the right lighting, like we have here in this ambient occlusion rendering, all of those pores are immediately visible. Every single one of them shows up as a dark tunnel in the rendered image. And because the ambient occlusion method it's sort of done using a hemisphere of sort of like if you'd put a hemispherical reflector around the surface, it provides light from all directions. And so things like pockets, pores, and cavities, these holes in the structure, they immediately jump out at you because they don't get, you know, they look very dark and they're always shadowed. And so this is something you can see immediately with this kind of lighting. And the user producing the figure doesn't have to put any effort into positioning light sources. If used regular directional lighting or positional lights, you'd have to adjust them, and you'd probably have to use a larger number of them in order to get these details to show up in a reasonable way in a figure like this. Whereas if you just use ambient occlusion lighting, it's completely automatic. So VMD has a lot of capabilities for making figures like you'd use on journal covers and in your manuscript figures. It has these rendering engines built in. And so you out of the box, installing nothing except for VMD itself, you have the tools needed to make figures like these. In fact, all of these figures, with the exception of this outer glass capsule, which was rendered with Houdini, everything else that you see on this page was rendered completely inside of VMD without any external tools at all. So, and then I think this light shaft was a Photoshop, but everything else was rendered inside of VMD. So these are examples of what you can do very easily just with what's in VMD itself. Any questions so far before I go on? I'm happy to answer any questions if anybody has one. So far, so good, huh? All right, fine. We'll continue then. If anybody has a question, feel free to raise your hand and we'll come back to you. So now I'll talk about some of the new features in the latest developmental versions of VMD. So I'm hoping that many of you have now tried the VMD 194 builds and are using those both for the tutorials this week and when you go back home and you run VMD at home. I'd suggest that you try out the newest versions. They have lots of new things. So some of the things that we've done most recently are update VMD to support Python 3. We have a number of different groups around the country that are big Python 3 users. And so the Python 3 support continues to get better and better as time goes on. We've made a lot of improvements to the structure preparation tools in VMD. For example, we just put in improvements to PSFGen that allow us to build structures of up to 1 billion atoms. Mariano can tell you about some of the things that he's done to improve molefacture, the quantum chemistry calculation tools. And of course, you've heard about the new versions of QuickMD and AlphaFold and so on. Some of the other areas that we're putting energy into are development of features for higher performance analysis of large data sets. So both trajectories, but also, for example, clustering analyses of large numbers of structures, whether they come from docking or from trajectories or from other sources. More features for processing density maps and tomograms, and a lot of additional new plugins. So I think you guys saw a nice demonstration yesterday of the Culver's dashboard by Jerome. And we have new features for interactive ray tracing, which I think Mariano is going to give you some nice demos of after this talk. Did I hear a question? That must be just a loose microphone.
There is a question about the GPU support for AMD graphic cards.
So GPUs, as far as GPU support goes, at the present time, all of the GPU accelerated analysis tools and so on are written using CUDA. And so right now they just support the NVIDIA GPUs. So AMD has developed a programming toolkit called HIP, which is compatible with CUDA. but it only supports the very, very newest AMD GPUs and only a very small fraction of them so far. My understanding is that their ultimate plan is that HIP will end up supporting all of the AMD GPUs, but at the present time, their focus has been on the computing-oriented GPUs that are found in the new Oak Ridge Frontier system. So these are these AMD MI100, MI60, and MI50 GPUs. That they're sort of the computing special versions. There's also an AMD Radeon 7. Those are supported by HIP. And so we have, for example, already adapted NAMD to support those GPUs using HIP. And I've discussed with the AMD developers getting VMD to support those GPUs also. But as I say, at the present time, their focus has been on computing oriented GPUs. So their tools don't yet support the normal AMD GPUs that you would have in a desktop machine. And so what we're really waiting for in the case of VMD is to have HIP support the normal mainstream AMD GPUs that you would buy for example, for video gaming. So for example, I have here at home an AMD Radeon 6700, which is one of the newer GPUs that just came out in the last 6 months, but it is one of the gaming oriented GPUs. And so it's not really supported by HIP or these other tools yet. As soon as they get that stuff working, then I expect to be able to support those GPUs using the HIP tools to cross compile all of these existing CUDA kernels and have them run on the AMD GPUs. So that's the plan for the AMD GPUs. Intel is coming out with new GPUs that are also in a similar way computing oriented. So the new Argonne National Laboratory Aurora machine contains Intel GPUs, or it will contain those Intel GPUs, but they're not actually available for sale yet. And it's sort of a similar deal. We're a bit about probably a year or 2 years ahead of when I would expect widespread support from Intel for these new GPUs that they're making. So really, at this point, everything that we're doing, we're talking about NVIDIA GPUs. We don't have anything against the other GPUs, but they are sort of playing catch up in terms of their support for the software tools and programming methods that we're using here. On the visualization side, there is something I'll tell you about at the end that with regards to particularly AMD and Intel for the visualization. There's some other ways we're going to support those that don't need CUDA or these other things to make them work. And I'll tell you a little bit about those at the end of this talk. Any other questions before I go on?
Yes, I do have a question.
Yeah.
So all these CUDA supported NVIDIA graphics cards, so those are not supported by the Apple, right? In Mac OS?
That's right. In fact, Apple is a special problem. Apple used to support OpenCL. So OpenCL was actually a cross-platform GPU acceleration standard that Apple actually submitted as a standard. So Apple developed it. And then as of about 2 years ago, when they were getting ready to bring out the new ARM-based Mac hardware, they announced that they were going to drop support for both OpenCL, which is what the standard that they developed themselves for cross-platform GPU acceleration, and also for OpenGL, which is what we use for interactive visualization in VMD and many other tools like Chimera and Pymol and everything else. So they announced this. They actually did drop support for OpenCL, and they don't support CUDA and haven't for about 5 years already. So there isn't any, in terms of macOS right now, there's really no good portable option for writing computing code. And so I would say that if you care about GPU acceleration, Apple is not a very good platform for that sort of thing. Their laptops are great and so on, but if you're wanting to buy a machine to do heavy number crunching, I would say that my advice would be avoid the Apple hardware for the number crunching stuff, because they're very weak as far as support for GPU acceleration goes. part of this is, I think their plan has been to displace AMD, Intel, and NVIDIA with their own proprietary graphics hardware. And the problem for them is it costs a tremendous amount of money to develop drivers and has, it's a huge engineering cost. And I think they just didn't want to have to do it, or they don't see the HPC market as being relevant for their customers. And so they've just decided to opt out and not pay the costs of doing that development work, at least for now.
Got it. Thanks.
Hey, real quick, I had a follow-up question.
Yeah.
So I wanted to ask what your thoughts were about other kind of low-cost computing parallelization options were. I've seen online that there are some options where people have built like cluster computers using like Raspberry Pis and stuff like that. And just for like implementing them in these labs that don't really have a budget dedicated to, getting a, like a Tesla core processor, but still want to be able to do that parallelization. Is that supported at all with these VMD or an AMD?
So I would say, yes, you could use something like a collection of Raspberry Pis, but in terms of the calculation per dollar, they would be destroyed by even a cheap gaming GPU. So this is the thing. Although you can definitely do that. And if you're doing it as a learning experience, for example, let's say you wanted to build a cluster not for the speed, but to learn how to run a cluster and how to write multi-node distributed memory parallel software, or how to deploy a program like VMD or NAMD on such hardware from scratch, nuts and bolts, those would be an excellent way to learn. But in terms of the value per dollar and the computing performance they achieve, there's no comparison. You would do much better to buy a gaming GPU. You don't have to buy a Tesla GPU necessarily, especially if you're on a budget. That's sort of out of the question, right? So you have to target lower end hardware, but even a lower mid-range gaming GPU will give you far, far, far more bang for the buck than even 30 or 40 Raspberry Pis. And they would be, the Raspberry Pis, while they're cheap, they'll add up to a GPU pretty quickly, and the GPU will still decimate the performance of a huge stack of Raspberry Pis. And part of the reason of, to be honest, it's not that there's something necessarily wrong with the Raspberry Pi processors, but in order to get good scaling, you have to have a very low latency, fast network. And that's something that a Raspberry Pi absolutely does not have. It has a limited PCI Express bus that isn't even the bandwidth that you would find on an x86 machine. And the networking that's built in is just Ethernet, if you're lucky, and it's not a particularly high performance Ethernet. So that's why I would say these are a wonderful way to learn and to practice these things like it before you would spend money on building a bigger cluster. This is a great exercise. You could, go buy 4 Raspberry Pis, set up a queuing system, learn how to do these things in your own lab before you do it with much more expensive x86 hardware, right? That's a great way of learning. But if you're looking to actually do production simulations, I would definitely go after commodity GPUs, and these gaming oriented GPUs will work just fine. Other questions?
Thanks.
All right, well, if not, then we'll continue, and that way we stay on track here. I got to keep track of the time, so we got about 20 minutes left. So some of the new tools that we've implemented in VMD for working with experimental density maps include a new MDFF plugin. So MDFF stands for Molecular Dynamics Flexible Fitting. I don't know if you heard about it earlier in the week or not, but it's one of the tools that's available. It's sort of a method that's developed in both NAMD and VMD together collectively. And sort of what these tools do is they allow you to do these flexible fitting simulations, so you can build higher resolution atomic structures that have the native conformations that you get out of cryo-EM. Some of the tools that are built into the plugin, so we have this easy to use graphical interface These are tools that have been in VMD for many years, but they didn't have a graphical interface. And so a lot of people were not aware that they even existed. So they will do things like rigid body fitting. So you can take an atomic structure and do the rigid body fit against a cryo-EM density map. We can calculate histograms, various map processing operations like trimming, clamping values, smoothing, noisy density maps, masking off parts of the maps that you don't want to use for your simulation or for your structure analysis. We can do segmentation of density maps. So if you look at the image in the bottom right corner, this is a segmentation of GROW-EL. And you might say, well, what is segmentation? That's basically a scheme by which we analyze a 3D density map and we assign regions of similar density values or connected regions of similar density values get assigned a unique index, sort of like it'd be like identifying the atoms that are in the same residue, right? If you're thinking of atom data. Here we're doing the same thing, but for 3D voxels. And by labeling those things with a unique index, we can then refer to them and we can say, I want to write out just the part of the structure that's in group 47, which might be this yellow region here, for example. And so that gives us the ability to refer to those parts of the structure directly. It allows us to do things like much like an atom selection, but for a volume. We can do cross correlation and potential calculations for MDFF using these tools. And so the main idea of this new graphical interface is it brings a lot of the steps that would be involved in preparing an MDFF refinement simulation into VMD itself, making the whole process simpler and requiring less software. So one of the things I've been working on a lot recently has been to improve VMD in terms of its abilities in large scale analysis. And so one of the things we're interested in doing is facilitating analyses of data sets that are so large that they won't fit into the onboard host memory of your compute node or your workstation. And for things that are so large that they can't fit in the onboard GPUs. So a lot of GPUs, these days GPUs have, let's say, 4 to 24 gigabytes of memory. A lot of the gaming GPUs only have, say, 6 gigabytes of GPU memory. And so what that means is if we have to do large scale analyses, we end up having to do a lot of disk IO, reading and writing trajectory files or structures of various kinds. One of the things we've done in the latest builds of VMD is teach VMD for the first time how to do IO straight from a disk into a GPU. And we can do that on state-of-the-art hardware platforms like the NVIDIA DGX2. This is a special machine that has 16 GPUs in a node, and they're connected by a high bandwidth switch internally. And we can do IO at rates of up to 70 gigabytes a second, which is tremendous. If you think about a moderate size all atom simulation with, say, 200,000 atoms, this means that we can process, on the order of 20 to 50,000 time steps per second of structures in that size range. We can read those time steps, do some math on them, and read more time steps until we've crunched through entire trajectories. So this is great. This comes up in things like clustering analysis. This is an example where if we want to identify key reaction coordinates in a simulation, we want to find stable poses in a protein folding simulation, for example, automatically, we might want to do a clustering analysis, but this requires reading every single frame in the trajectory. And we have to do an RMSD calculation of every one of those frames against every other frame. So we have sort of an n²/2 calculation, but more importantly, because we probably don't have enough memory to hold all those trajectory frames, we're going to have to do all that in IO. And so that's a tremendous amount of disk IO we have to do. And it's interesting to point that out because with the acceleration we get out of GPUs, we're actually memory bandwidth bound. So the GPUs actually are so capable in terms of doing floating point arithmetic. It's not the arithmetic that's the limiting factor for performance. It's how fast we can feed them with the data. And so working on that stuff with the state-of-the-art machines we have now, If you build a new computer today with the latest CPUs, you can have PCI Express 4, which gives you up to 32 gigabytes a second of IO. If you combine that with state-of-the-art SSDs and things like GPU Direct IO, now we have enough technical components that we can really do out of core analysis on a large scale in a systematic way. And it's nice that we can do it at 70 gigabytes a second on a machine like a DGX2, but what we also care about is what can you do on your desktop machine? And so all the things that you see here are sort of commodity technologies. You already have, if you build a new computer today, you're going to have PCI Express 4 without trying. If you build a new computer today, it'll probably have an SSD. If you're lucky, it's NVMe. And GPU Direct IO, if you have an NVIDIA GPU, these will all work out of the box. And so this is great. So then what we want to do is now take a step forward. With these technologies, we have new opportunities we never had before. But one of the problems is VMD, the way that VMD does analysis today is sort of based on how things were over the last 25 years. And there's not enough concurrency in the imperative programming scheme that we use. We issue a command like calculate an RMSD for frame X and frame Y. Sorry, somebody had a question? I guess not. Anyway, so you issue a command to perform one of these analyses. That's great, but by issuing those commands, we're actually limiting how fast something like a GPU can calculate, and the rate at which you execute those commands ends up being a bottleneck. So what we really want to be able to do today is to queue up a large amount of analysis work in some sort of a to-do list, you might say. And we want to express that as a workflow or a graph of nodes, which are operators, and edges, which are transfers of partial results or information between different steps in the analysis. And we want to provide all of that to VMD upfront. And then one of the things we can do is VMD can analyze all the calculations that you want to do. And in a single pass over these trajectory files, it can basically grind through doing all of the analyses at once. And this gives us the maximum opportunity to use multi-node parallelism on a supercomputer or even on a desktop machine. This lets us use, let's say you had 2 or 3 GPUs, you'd be able to use them all effectively, even doing multiple different analysis calculations at the same time. And so right now we're sort of envisioning how that would work, and we have to sort of invent new schemes to do this. And this isn't really a limitation that's unique to VMD. Every existing molecular dynamics software analysis tool has these same issues because they were developed during the same time frame with the same technologies at hand. And it's only now that we really have the opportunity to do something different. And so this is very exciting for us with VMD and NAMD. So yeah, and I would say then the last stuff I'll talk about, we have about 8 minutes left, is GPU accelerated ray tracing. So I told you a little bit about this at the beginning. We've been doing a lot more recently with things like remote video streaming. So this allows you to run VMD on a powerful compute node somewhere else, like a remote supercomputer, and to stream the video back to a VMD instance or a client instance running on your desktop or laptop computer. So this can let you work on very large structures at a distant location without moving the file. So this is a new feature we're working on that's sort of visualization specific, but that's something that's an ongoing project, and I expect we'll have a lot more to say there as time goes on. We have all these built-in rendering engines because they give us much higher performance than what we would get if we used external tools like Blender. A question that I often get is, why do all this ray tracing stuff in VMD? Why not just export the scene to Blender? One of the reasons is by keeping the scene data inside of VMD, VMD knows what all these atomic structures are. It can represent them in the best possible way, both in terms of the geometric primitives used to render it and also the way that those geometric primitives are written into memory. And this allows us to do things like render these billion atom structures, like the examples I've shown earlier, and some you'll see here in a minute. And that's something that we wouldn't be able to do with outboard tools. There are still purposes, like one might ask, well, when is it the right thing to use something like Blender? And I would say the main thing you get out of visual effects tools like Blender is stuff like camera choreography. If you want to make a really complicated camera flight path, that's a good use of Blender. But if you want to make a sophisticated molecular visualization, then doing it internally in VMD is definitely the right way to go. So there are sort of different answers for different use cases, and I'll talk about those later. VMD exploits the state-of-the-art GPUs that have hardware acceleration for ray tracing. And some of the things we get out of that are huge performance increases just from one generation of GPUs to the next. So if you look at just NVIDIA's own GPUs, what had been their highest end GPU previously was the Quadro GV100. That was a commercial, high-end visual effects oriented GPU that they would sell to the Hollywood types. Most of you probably had GPUs that were less powerful than this. We went from a relative speed of 1 on a Quadro GV100. The first generation RTX acceleration with the Turing generation of GPUs for the same scene, you can see right here, this is a transparent photosynthetic organelle with a large number of internal surfaces, transparent geometry, and so on. Going from this, with that scene going from a GV100 to a RTX 6000, we get a factor of 8.7 speed up. That's a tremendous speed up just due to the new hardware acceleration of ray tracing. Same thing calculated for this other scene here. This is another photosynthetic organelle rendering with a bunch of instances of the same organelle. So this is a few hundreds of these structures. So this is representing some billions of atoms here. This is a speed up of about 5. And the main difference is what fraction of the scene are things like spheres and cylinders, and what fraction are triangles. The scene on the left is primarily made of triangles. The scene on the right is about 50-50. And so it gets a little bit less speed up because the state-of-the-art GPUs do more to accelerate triangles than the other geometry. We used some of these techniques to render Birth of Planet Earth, which was a dome planetarium show that included a component on photosynthesis. And so we made a special renderer in VMD for planetarium dome projections. We went back and compared the performance. We did that entire dome show using Maxwell generation GPUs. So like the GeForce 900 series, like we use GeForce 980s and Quadro M6000s. If we did the same dome show today with the latest RTX GPUs, it would be up to 15 times faster just due to hardware acceleration. The speed that we get out of the hardware now means we can do all kinds of interesting things, like we were able to do omnidirectional ray tracing to make VR movies for YouTube. Those can be done offline, but we can actually, with state-of-the-art GPUs now, we can run these things fast enough that you can actually feed a VR headset in real time. We did this before with custom written software, and we're working on now making that work more generally with the currently popular commodity VR headsets, such as those from Oculus and the other companies. As you know, the size of the structures we're simulating goes up every year. And so a big concern is how are we going to be able to, continue rendering things like these large billion atom structures with the limited memory of GPUs. And so we put a lot of energy into optimizing the rendering engines in VMD to make them very memory efficient. So this is a rendering of the SARS-CoV-2 virion from a project we did last year with Romy Amaro's group. This is using the GPU ray tracer in VMD. This is a 305 million atom simulation of the full virion with all the spike proteins, and you can see detailed renderings of the individual spikes. Another thing that you'll hear about today is a new rendering mode of VMD where we add real-time ray tracing for the first time as an alternative to OpenGL. And so that means for the first time ever, and nobody outside of our lab has seen this at all until this week. So you guys are the first to really get a presentation about it in a workshop. So now for the first time, there's a Linux version of VMD that supports full-time real-time ray tracing instead of OpenGL. There's a new display mode. And if you look at the bottom of this figure, basically we have a new ray tracing engine that displaces OpenGL. So all this stuff in green is a new piece of software that didn't exist before. And that means you can make figures like the ones that we've been showing, not only for a static structure, but you can even play back a trajectory and do all the other things that you're accustomed to in VMD. So this is a very new feature and it's still in development, but I wanted to make you aware of it. And I think Mariano will give you a demo in a few minutes. One of the last things I wanted to say is, aside from the built-in renders we already support, including the ones that I wrote, one of the things that's going forward is VMD is going to be connected to a bunch of high-end renders that are more either cross-platform renders written by the hardware vendors themselves. I mentioned that even aside from the issues with CUDA and macOS, there's an opportunity for us to tie in high-end renderers from AMD and Intel that support their hardware, even on platforms like macOS. And one of the ways we're going to do that is through a new standard called Inari, which provides cross-platform high-fidelity visualization for applications like VMD. And this is an early example of the types of rendering we can do with the different engines that already exist. These are all prototypes. And this is with a developmental version of VMD, but you can see the same satellite tobacco mosaic virus scene rendered with the built-in tachyon ray tracer that's standard in VMD, and comparing the results we get with path tracers written by Intel. This is the Intel Osprey path tracer, and this is an optics path tracer written by somebody at NVIDIA. There's another a new toolkit for AMD GPUs called Radeon Pro Render, and there's an early version of that that's coming out too. And so I expect this will be one of the ways we support all those hardware platforms, even on operating systems like macOS, for example. Another cool thing will be, aside from Blender, I mentioned, for some of the things you might want to do fancy camera choreography, NVIDIA has a new tool called Omniverse, and we're working on a direct link between VMD to allow VMD scenes to be imported directly into Omniverse, and that'll allow you to use really sophisticated material properties like these ice materials and things like this, more biological appearing materials in their production renders, and you'll be able to do fancy camera fly-throughs and things like that more easily than you would in a normal scientific visualization tool like VMD. And with that, I'll take any last questions. No questions, really? Well, how about I stop sharing, and Mariano, you can get prepared. And if anybody has questions, I'm happy to answer them while we have time.
Sorry, I have one question.
Yeah, go ahead.
Apple came up with this M whatever.
Yeah, it's an ARM. It's an ARM chip.
So this VMD gonna be compatible with that, or like?
Yeah, we have test builds of VMD for the. We have test builds available for the Apple M1 chip already. They're posted now. They've actually been available for 6 months already. We continue to make new improvements as Apple keeps changing the software for the M1, but VMD is running on it. I have an Apple M1 test box here, and so I continue to work on it here every day. Do you have any particular questions about the M1?
None right now, but I will get in touch with you whenever things come up, because I'm just trying to see because one of my lab mates tried to user had some issue. I don't remember the specific, but there was some compatibility issue with it. It could be the Mac, what do you call the M Pro? They had M Max, M Pro type of thing. You know, they keep changing it as you say. So that
There's
might
a,
be the
yeah,
case. Yeah.
I think we can expect that, you know, the M1 hardware and software are completely new. So, you know, and it's all Apple's stuff. So that means they're writing all the software. So things like graphics drivers are changing very quickly. They're releasing updates at a feverish pace to, you know, to change many things about the M1. I do know that there have been issues where people had to launch VMD from the command line rather than double clicking on the icon on the M1, because Apple has decided to restrict the ability of external software that wasn't obtained through the Apple Store. And so this is something that's outside of our control at the present time. I don't know if we'll find a workaround for that or not, but if we don't, then it may end up being that the new way of launching VMD for an M1 is just to run it from the command line rather than clicking on the icon. But other than that, it should work fine.